All right, let's dive into one of the most incredible, most shocking discoveries in the history of science. This is a story about how scientists, looking at the faintest, most distant exploding stars, accidentally stumbled upon a secret that completely rewrote our understanding of the entire universe. You know, ever since we figured out the universe is expanding, there's been this one huge question hanging over everyone's head. How does this all end? Is the expansion going to slow down, maybe even reverse itself and come crashing back together? Or does it just go on forever? For most of the last century, the answer seemed to depend on just one single thing. And that one thing was gravity. I mean, the logic seemed pretty simple, right? The universe is packed with stuff. Galaxies, stars, you name it. And all that stuff has gravity. It's like when you throw a ball up in the air. Gravity slows it down. So the combined pull of everything in the cosmos should be putting the brakes on the expansion from the Big Bang. The only real question was, well, how hard is it hitting the brakes? So this gave scientists two main possibilities. If there was enough stuff out there, enough gravity, the expansion would eventually stop, turn around, and everything would collapse in a fiery end they called the Big Crunch. Yikes. But if there wasn't enough stuff, the universe would just expand forever, but it would always be getting slower and slower, just kind of coasting into infinity. To figure out which story was true, they had to somehow measure the history of the universe's expansion.
Okay, so how on earth do you do that? You need what astronomers call a standard candle. Think of it like this. Imagine a long, dark street lined with identical 100-watt light bulbs. You know exactly how bright each one really is. So if you see one that looks super dim, you know it's just really, really far away. The dimmer it looks, the farther it is. They needed to find a perfect cosmic light bulb, something so bright and so consistent they could spot it from billions of light years away.
And that's where this amazing thing comes into play, the Type 1a supernova. Now, this is a very specific kind of explosion from a dead star called a white dwarf. And here's the magic part. They almost always explode with the exact same peak brightness. They're unbelievably reliable. They were the perfect tool, those cosmic light bulbs astronomers had been dreaming of. So the logic here is just beautiful. You find one of these explosions in a galaxy far, far away. You measure how faint it looks to us, and because you know how bright it's supposed to be, the difference tells you exactly how far away it is. If you do this for a bunch of supernovae at different distances, you can literally draw a map of the universe's expansion history and see if it's slowing down like everybody thought it was. So in 1988, a team called the Supernova Cosmology Project, led by a guy named Perlmutter, decided, all right, let's go do this. They had a really ambitious mission, find and study dozens of these incredibly faint, distant supernovae to finally measure just how much the universe was slowing down. It took them years just to figure out how to even hunt for these tiny, fleeting flashes of light. After years of painstakingly hard work, using the most powerful telescopes on Earth, the team finally had their data. 42 very distant supernovae. They were all set to plug the numbers in and get their answer. They were expecting to finally pin down how much gravity was breaking the universe. But the answer they got was, well, it was impossible. The data didn't fit any of their models. Here was the problem. In any universe that was slowing down, those distant supernovae should have looked a certain brightness. But that's not what they saw. Over and over again, the supernovae they found were fainter than they had any right to be. And we're not talking just a little bit fainter. They were about 15% fainter than expected. Now, in cosmology, 15% is a huge deal. That is not a rounding error. So of course, they thought they'd messed up. They checked for dust, problems with the telescopes, flaws in their math. They checked everything. But the result wouldn't go away, which led them to a terrifyingly simple question. What if the supernovae weren't the problem? What if they were perfect standard candles? Well, if they're fainter than they should be, that can only mean one thing. They're farther away than any of the models predicted. But how could that be? What could have possibly pushed them farther away from us over all those billions of years? The team was forced to think about an idea that went against everything they knew, an idea so out there that most physicists had dismissed it for decades. But it was the only thing that actually fit the data. The universe wasn't slowing down at all. It was speeding up. The expansion was actually accelerating. That's why the supernovae were fainter, because in the billions of years it took their light to reach us, the universe had stretched out more than anyone expected, pushing them farther away. It meant there had to be some kind of mysterious anti-gravity force built into the fabric of space itself.
And you can just feel their confidence right in the abstract of their paper. That little symbol, lambda, stands for the cosmological constant. It's an old idea Einstein had about an energy that exists in empty space. And they basically say, our data shows with 99% confidence that this thing is real, it's there, and it is actively pushing our universe apart. It was a total mic drop moment for science.
So look, this discovery didn't just tweak our picture of the cosmos, it blew it up entirely. The entire inventory of what the universe is made of had to be ripped up and started over. Everything we can see, all the stars and galaxies, turned out to be just a tiny piece of the puzzle.
Their data pointed to this absolutely wild new picture. You take all the matter that we know about, even dark matter, and it only adds up to about 28% of the universe. The rest of it, a mind-boggling 72%, is made of this mysterious dark energy, the very force that's driving the acceleration. We were living in a universe where the main ingredient was completely unknown to us.
And the fallout from this was immediate and profound. First, an accelerating universe meant it was older than we thought, about 14.9 billion years old. This actually solved a nagging problem where some stars seemed to be older than the universe itself, so that was a relief. Second, it decided our ultimate fate. No big crunch. Instead, we're headed for a cold, dark, lonely future of endless expansion. And third, it handed us the biggest mystery in all of physics.
Think about it. In 1998, astronomers went looking for the breaks on the universe, and instead, they found that 70% of it was something they never even knew existed. This discovery, which absolutely earned a Nobel Prize, answered that ancient question of the universe's fate, only to replace it with a much bigger, much stranger question. What is this dark energy? And all these years later, that is still the biggest question in all of science.